You are listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists who are going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Wurth Elektronik What's Up podcast. Today's podcast is a continuation of last week's segment on power inductors and comes from our webinar, Power Up with Power Inductors. Now again, this is not the same webinar from George Slama. This one is a bit more advanced. Finishing up our topic today is Maximiliano Padilla, Technical Chat Navigator with Wurth Elektronik Online in Mexico. Max began last week's podcast on defining the inductor and inductance and the Q factor, then moved on to the construction of the component. He then covered the basics of core materials and what to consider when designing specific applications. And today we finish with the construction of an inductor, specifics and differences in wires, and discussing the skin effect. Enjoyed today's presentation, Power Up with Power Inductors.
Now that we have covered the basics of the core materials and what to consider when deciding for a specific application, let's go ahead and talk about the wire and its characteristics. One of the main concepts when we discuss the wire of an inductor is the direct current resistance, commonly found as DCR on the datasheets. We can define this concept as the resistance of an inductor as a result of the resistance of the wire used in the winding. On the following slides, we're going to review how to calculate this resistance value given the two main types of wires, round and flat. You might wonder, which one's better? Well, this entirely depends on the application. There are also a couple of wire characteristics that are going to define the inductor's behavior. This would be the physical size related to the resistance, which affects the current and temperature. The frequency, which is going to produce a skin and proximity effect. And the insulation class, which relates to the voltage. First, let's tackle how to calculate the DCR value on a round wire, which might be the most commonly found. For these examples, we're going to be using a copper wire with a resistivity of 1.68 to the power of -8. This value is assigned to the Greek letter rho, and it is measured in ohms per meter. We would also need the length of the wire, which is the letter L on the formula, and the cross-sectional area, which is A. In order to calculate the direct current resistance, we must use the shown formula and always remember to convert all parameters to meters. First of all, let's propose a diameter of 1 millimeter, as shown on the little yellow circle on the bottom left corner. We can easily calculate the cross-sectional area with this information. We take the 1 millimeter diameter squared, multiply it by pi, and divide it by 4. That's how we get the 0.78 square millimeters as the cross-sectional area. After this, we can substitute the values on our formula, as shown on the right side of the slide. We must multiply the resistivity of copper times the length of the wire, which for this example is 1 meter, and finally dividing this result by the cross-sectional area that we have previously calculated. The final result would be 21.5 milliohms for the direct current resistance when there is a 1 millimeter diameter. As you can see, the bigger yellow circle on the bottom left corner shows a diameter for 2 millimeters, And we've applied the same calculations and we got the following results. The cross-sectional area is 3.14 square millimeters, and the direct current resistance would be 5.35 milliohms, which is around 4 times smaller than the previous calculation. And this is considering the same wire length and material. With this example is shown that the bigger the diameter, the bigger the cross-sectional area. Therefore, the direct current resistance would be smaller. Of course, you could adjust any of these variables in order to get different DCR values. This formula is quite helpful for this. Okay, so now that we have shown how to calculate the DCR value on round wires, let's dive into flat wires. For this example, we're once again using copper as our wire material. This means that the resistivity rho stays the same, 1.68 to the power of -8. Also, we have a 1 meter long rectangular shaped wire with a cross-sectional area of 4 square millimeters. The width of this rectangle measures 4 millimeters and it is 1 millimeter in height. As you can see, the same principle applies, and formula, of course, in this type of wires. On the right side, you can see the procedure to calculate the direct current resistance. We must multiply the resistivity of copper times the length of the wire, which for this example is also 1 meter, and finally dividing this result by the cross-sectional area that we have previously calculated. The final result would be 4.2 milliohms, which is a bit lower than the 2 diameter round wire on the previous example with 5.35 milliohms. So now that we have calculated the direct current resistance for both types of wires, round and flat, you might be wondering why we got these results. And the answer is, this is entirely related to the cross-sectional area that both geometric shapes possess. The following example shows the comparison between both shapes with similar dimensions. We have the yellow circle with a 1 millimeter diameter and a blue square with each side measuring 1 millimeter. Due to these geometrical properties, the circle has approximately 78% area compared to a similar width square, meaning that the circle loses about 22% surface area. This is shown on the right figure when we overlap both shapes. Each square corner has around 5.5% more area. So this is the reason why the yellow circle has a cross-sectional area of 0.78 square millimeters, and the blue square has a slightly bigger value, 1 square millimeter. Since this value is higher, the direct current resistance value would be lower, as shown below, with 21.5 milliohms on the yellow circle and 18.3 milliohms on the blue square. Great, so let's go back to the basics and quickly recap this information. As the cross-sectional area increases, the direct current resistance is reduced, as shown on the graph. In other words, the direct current resistance is inversely proportional to the cross-sectional area of the conductor. The larger the cross-sectional area of the conductor, the more electrons are available to carry the electric charge, hence the low resistance. You can see below the 3 examples that we have previously analyzed. There is another important concept to talk about when we refer to frequency, and alternating current losses. This is called the skin effect. For single isolated conductors through which high frequency current flows, current only flows on the outer skin of the conductor. In other words, as we increase the frequency, the current starts to get pushed on the outer wire layer, which means that it has less space or area to flow through. The yellow figure on the right shows the cross-sectional area of a round wire with diameter d, radius r, and penetration depth delta. Most current flows on this outer ring delimited by the delta value, or as we call penetration depth. In order to calculate this penetration depth, we would need to have the permeability and resistivity of the wire material. Also, the angular frequency, which can be calculated by multiplying 2 times pi times the frequency of operation. For this example, we're going to be using copper as our wire material with the shown properties. We would only need to follow the shown formula in order to obtain the penetration depth, which for this example is measured in meters. Great, so let's evaluate the skin effect in an application. If we have a buck converter with a 250 kilohertz frequency and we're using a round copper wire, this would be the way to calculate the penetration depth. First of all, we take the resistivity of copper, ρ, and multiply it by 2. After this, we would need to divide it by the result of 2 times pi times the 250 kilohertz frequency times the permeability of copper. The result would be 17 to the minus 9th power, which we would need the square root. After substituting the values in the formula, we have that the penetration depth for this buck converter would be 0.13 millimeters. So what does this mean? The following diagram shows the current distribution in a conductor at various frequencies. As this frequency increases, the skin depth decreases, and the cross-sectional area decreases as well, therefore increasing in resistance. You can calculate this cross-sectional area by multiplying 2 times pi times the radius times the skin depth. The diagram shows 3 examples of this skin effect. As you can see, at 50 Hertz, we have a 9.38 millimeters skin depth. If we increase the frequency to 10 kilohertz, the skin depth would be less, 0.66 millimeters. And finally, if we increase it to 400 kilohertz, the skin depth would be even smaller, 0.1 millimeters. The area at which the current flows is going to be limited by this value. This is something very important to take into consideration when handling high frequency values. With that said, let's talk a little bit more about the rated current. Wurth Elektronik defines rated current as the current that causes the inductor to heat up above ambient temperature due to self-heating. This is different from saturation current and may be a larger value. For example, if an inductor is operated at its rated current, it means that it heats up above the ambient temperature by the temperature stated in the datasheets. In our components, this stated temperature is typically 40 degrees Celsius. However, magnetics industry is not standardized, and not all manufacturers use the same testing parameters on their datasheets. This is always something you must take into consideration when comparing inductors between different competitors. The diagram on the right shows our measurement setup to determine the rated current. We place the inductor with a sensor on a testing bench and power it with, of course, a power supply. We use a temperature sensor device to detect the ambient temperature and the inductor's temperature. All this information is analyzed and saved in a computer. And finally, let's discuss the self-resonant frequency. Every inductor has a capacitive coupling arising from its winding turns and multiple layers. These parasitic capacitances are symbolized by a capacitor C in the equivalent circuit shown on the top right diagram. This capacitance in the coil forms a parallel resonant circuit with the inductance. The self-resonant frequency, or SRF, is the frequency at which the parasitic capacitances of the inductor resonate with the ideal inductance of the inductor. The input energy oscillates back and forth between the elements of inductance and capacitance. The inductor only functions of the self-resonant frequency. If the inductor is operated above its resonance, the capacitance dominates, and in fact, the inductor acts as a capacitor. This is why they should always be operated below their resonant frequency. Also, at the self-resonant frequency, the impedance becomes very high, and the inductor can be used as a EMC filter choke. Take in mind that the higher the number of turns around a core will result in a higher inner winding capacitance. Therefore, this shifts the self-resonant frequency into the lower frequency spectrum.
This podcast was taken from a Wurth Elektronik webinar. To view the materials and replay the webinar on demand, simply click the link attached in this podcast. Now, as mentioned before, our presenter, Max, is a technical chat navigator at Wurth Elektronik Online. You can chat directly with Max and the team by clicking the chat icon at www.we-online.com. You're listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Wurth Elektronik technical specialists. We're going to shine a light on topics like energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Wurth Elektronik What's Up podcast.